Hi, I'm Kristina Cohen, SPA President. Welcome to this year's Nicolet Lecture, where we honor one of our community for their significant contributions to the area of aeronomy. I will now hand you off to Ron Hampton, who has the pleasure of introducing this year's honoree.
Hello, I'm Don Hampton from the Geophysical Institute and Poker Flat Research Range at the University of Alaska Fairbanks. When I tell any fifth grader who happens to ask what I do for a living, the reaction I get is typically, "You get to work with rockets? You have the best job in the world." I hardly ever disagree with that statement. And while I try to embrace my inner fifth grader and really love the acceleration of the countdown, the thrill of the launch, and the breathless anticipation of the stream of bits coming back from the payload, I've learned that those moments, while important, are fleeting. And what really lasts are the interactions with a group of amazing and talented people who make up the sounding rocket and overall aeronomy community. Today's speaker is a prime example. Professor Kristina Lynch has an impressive resume. She graduated with an undergraduate degree in physics from Washington University in St. Louis, spent 4 years at the Air Force Geophysical Lab when it was in Massachusetts as a lieutenant in the Air Force. She then received a master's in physics from University of New Hampshire and then a PhD in physics just 2 years later. From 1992 to 2002, she worked in a research track position at University of New Hampshire, ending as a research associate professor. In 2002, she moved into a tenure track position at Dartmouth and is now professor of physics and the chair of the Department of Physics and Astronomy at Dartmouth. Her research in aeronomy has primarily involved using data from in situ space plasma instruments to understand how the magnetosphere, ionosphere, and thermosphere interact and influence each other in various forms of the aurora. In many cases, the instruments were ones that she designed and built. For example, she built particle detectors for the CREST mission with AFGL, and more recently has been fielding sets of petite ion probes, or PIPs, to measure the thermal properties of in situ plasma, as you will hear in her lecture. This instrumental expertise has led to a significant presence in the NASA Sounding Rocket program, as co-investigator on 11 projects and principal investigator on 5. To sustain this development effort, she has built and maintains a sophisticated sounding rocket instrumentation lab in the nooks and crannies of a 19th century building at Dartmouth, including a large thermal vacuum chamber for instrument testing and qualification. You don't build instruments or plow through the data they produce single-handedly. So to support these ambitious development and associated analysis efforts, Kristina has mentored 12 PhD students, another 12 senior honors thesis students, and over 50 undergraduate researchers. Many of these students have gone on to make important advancements in their own careers. She has also contributed to the aeronomy community by adding her perspective on aurora and ionospheric processes on several planning and review committees, including the National Academy's Heliophysics Decadal Survey in 2011 and NSF's Geospace Portfolio Review in 2015. So how does she do it? What is the recipe for achieving all these successes? From what I can tell, she starts with laser sharp focus and concentration on a topic and adds in a bit of dogged determination. She mixes in a healthy dose of inclusiveness for students and colleagues, bringing them together, not just as a group of peers, but as a part of a team. And most importantly, the foundation of the recipe is that she fully embraces her inner fifth grader. That insatiable curiosity and the utter joy of discovery are alive and well in Kristina, and they are the key ingredients in making a great scientist. Ladies and gentlemen, it is my pleasure to introduce this year's Nicolet Lecturer, Professor Kristina Lynch.
Okay, I'm happy to talk to you today about exploring neurospace with sounding rockets. I'm Kristina Lynch from Dartmouth College, Department of Physics and Astronomy. I want to talk about multiple point sounding rockets, and this image is sort of the epitome of multiple point sounding rockets. It's a photograph of some releases from 2 separate rockets over Scandinavia. Each of the rockets carried 24 separable payloads, and each of those separable payloads released chemicals as tracers in the ionosphere and the atmosphere. The upper purple clouds are neutral barium and strontium, and you can see that when that ionizes, that plasma separates and aligns to the magnetic field. The teal and white down below are TMA that gets entrained in the atmosphere. And so this pixelization of the plasma and the atmosphere allow us to understand and learn about how the ionosphere evolves. But this image is a beautiful representation of how we use multiple point sounding rockets to explore near-Earth space. This picture is why I do what I do. This is an image from Venati, Alaska, under the apogee of one of our recent sounding rockets out of Poker Flat Research Range. And what we're trying to look at with distributed measurement points of the auroral ionosphere is to try and understand how the aurora does, what it does. But it's a beautiful thing. How we do it is we use sounding rockets. And here is an image of a two-stage rocket launch. You see the motor burn, and then that motor is detached and dropped, and then the second motor goes up to here. This is an image from Poker Flat, so you can actually also see in the background here the LiDAR from the imaging center, and you see the northern lights. So I'd like to share with you today a non-comprehensive tour of sounding rockets on the night side in the auroral zone. Sounding rocket platform lets us try some crazy things sometimes. I'd like to get across the premise that it's a lot of hard work, but it's also a lot of fun, and it's scientifically useful. So I'll take you through some history of the multiple point sounding rocket world, talk a little about the teamwork that makes it possible, and the distributed observations that are our goal. And then, again, in a non-comprehensive way, take you through some example science cases of how we've used this platform to explore the ionosphere. I'll finish up with some ongoing work and a summary. So one of the things you find in science, of course, is that everybody's done it before. And so people have been doing multiple point sounding rockets for a long, long time. When I asked my sounding rocket colleagues for examples, Rob Pfaff was quick to tell me I have to make sure to start with porcupine. Back in the 1970s, Professor Harrendell had an experiment called porcupine because it had so many things sticking off of it. It looked like a porcupine. It carried 11 experiments, 12 booms, 2 self-contained probes, and 2 explosive charges to explore its environment. The last time I was in Andenes, I was talking to some Norwegian about what were these things. And so back in 1980, the Norwegians were building what are called dropsondes. So little softball-sized electrometers surrounded in a metal mesh. Each one of these little spheres was dropped from the rocket and had a whip antenna to telemeter, a radio antenna to telemeter its information to the ground. And Tom Arnold-Blix tells me about those dropsondes that at apogee at 130 kilometers, the two were separated by 600 meters. And then at 70 kilometers on the downlink, they were separated by 1,200 meters. And what they found is that the probe data lost correlation with each other around 300 or 400 meters apart. And they interpreted this as the probes being in different turbulence areas, different whirls. So all the way back in 1980s, people were already exploring throwing things off of sounding rockets to make distributed observations of the ionosphere. Where I came into things was the Echo 7 experiment in the 1980s. And so here is a bunch of crazy people who decide to send an electron beam to the other hemisphere and catch it when it bounces. And so my first exposure to a sounding rocket payload involved going down to the basement at AFGL and seeing this, you think that sounding rockets are fancy, glorious things. This was basically a stack of car batteries. So the main payload was about as big as me, and all the decks had car batteries in them. And so this main payload here mostly was a set of batteries to supply this electron beam, which would go all the way down to the southern hemisphere, bounce from the mirror force, and come back a few seconds later. And then because of E cross B drift, they had to have a distributed set of observations. And so we see that this Echo 7 payload configuration involved the main payload, an observing TV camera payload, another payload, and another payload. It also had a tether, and the camera showed the electron beam leaving the main payload. And they were able to show that the diagnostic payloads could see the correlation pattern in the beam that was recording, coming right back. So it makes the idea of the dipolar shape of the Earth's magnetosphere very, very real. It's not a hypothesis. You're actually sending an electron beam and watching it come back. The other fun thing about the Echo 7 experiment, so this was my first opportunity to go to Poker Flat in Alaska. I got to meet Professor Winkler from Minnesota, who was a very small and at that time apparently a very ancient man. And while the rest of us would walk up the hill at Poker Flat to go to the old science building, which granted is only half as far up as it is now, Professor Winkler would run up the hill. And so he was very dedicated to his work. The other fun thing about being there is I traveled with a recent PhD student from Boston who had just spent 6 years of his life writing a theoretical thesis about the Northern Lights. And so every night when we would drive back from Poker Flat back to Fairbanks, it would take us about twice as long as everybody else, because every time there was an aurora, we would have to stop so the student could get out and see it. And so it was exciting to learn about the Northern Lights with people who were so dedicated to their work. And so after that payload with all of its batteries, I was hooked. And I can take you through a tour of a lot of these multiple point rockets. People call them different things. There was Auroral Turbulence 2 with its throwaway detectors. There was the Cornell sequence, Amethyst, Sierra, Mica, that had the Cowboy. So here's a picture of the Cowboy payload. Which is a large and very beautiful payload. It's the full size of the rocket, and then it has a subsidiary cylinder which rotates with respect to the main one. So this object gets thrown away from the payload, and then the wire booms on this small cylinder spin out. So this small cylinder is actually a turkey fryer from a hardware store. The Cornell lab had boxes and boxes of these things for many years. And then in between this cylinder and this cylinder is a magnetic brake from an exercise bicycle. So a lot of ingenuity goes into building up these diagnostic payloads. So as the two cylinders rotate with respect to each other, the wire booms fold out. And in the end, they are 12-meter tip-to-tip double probes. And so working with these payloads, you do get distributed measurements, but they're large. And so we explored making smaller distributed payloads so that we could have a lot of them. And so we got to work with JPL for the hockey puck rocket. So these were 4 small, literally hockey puck size sounding rocket payloads that were used to make a curl of B measurement. And one of the things we learned there is it's hard to make things really small. This would have been twice as easy or 10 times as easy if these were maybe twice as large. We went on then to the pulsating aurora experiment that had flyaway detectors. Cascades 2 had Cowboys and particle-free flyers, more Cowboys, and then the more recent ones build on the structure that I showed in the first slide. So those chemical releases have small cylindrical subpayloads that are deployed from the rocket. And once that deployment system got set up, we got interested in, could we put telemetry on it rather than just blowing them up as chemical releases. And so our group went through a small payload development and created a telemetry payload called a Bob, which was flown on the Icing Glass rocket. And then most recently, the NASA and NASROC community has taken over the power and telemetry part of that small payload. And now instrumenters are just building what we call boblets, which is the front end. And so here are 3 that we're building for this winter's rocket. So how does this work? It takes a lot of people and a lot of dedication, a lot of crazy people who are really dedicated to what they do. We spend a lot of time in cinder block rooms with fluorescent lights, whether it's in Virginia or Norway or Poker, Alaska, they all kind of look like this. And you get people who are just really, really focused on the work that they're doing, and it's fun. It's fun to work with them. How we get there? Lots and lots of lists. We have checklists, we have parts lists, we have test lists, we have lists of lists, lists of lists of lists, and we do a lot of testing. The rocket's only up there for 10 minutes. You don't have time to fix it in the process. It has to work beforehand. So we have systems test, vibration test, the bend test is the scariest thing. You build up the rocket, you bolt it to a fixture, you grab the top of the rocket and you bend it and make sure that it's not going to snap during the load of passing through the atmosphere. RF test for radio noise, GPS test to make sure that your GPS receiver works, magnetic calibration test, sequence test, the list goes on and on. And then the way we get there is with our people. So technicians, engineers, students, scientists, managers, machinists. So here's a picture of the Dartmouth group and all of the parts that we delivered for the Icing Glass campaign. The left side of the table is one of the rockets, the right side of the table is the other rocket, and the middle is the spares. So these are the 4 Bob payloads that each rocket deployed and some main payload experiments. So I have my list of what bad rockets do to you. Bad rockets blow up. Sometimes they burn at both ends. That's exciting. Get a firework. It's not fun. Also, bad rockets don't ignite. They get up there, they don't light up, they fall back down. They fly 3 sigma to the left. You want to go north, they go east. They vibrate a lot, break things. They go into flat spins. High voltages fry and fritz and do other things. Things don't deploy, open, unfold, release, or separate, or they do deploy, open, unfold, release, and separate, but they do it at the wrong time. So there's many, many ways. As they say, bad families or happy families are all alike. Unhappy families are all special in their own way, as they say. But good rockets are, as they say, a great 10 minutes. They provide an in situ case study that you can put where and when you want it in a finite amount of time. Often the sounding rocket mission can go from conception to design to implementation to analysis within the span of a graduate student lifetime. So students can be very involved here. Importantly, launching a rocket is real-time space weather. You really learn to appreciate how the auroral ionosphere is going to evolve when you have to decide when to launch your rocket. These multiple point missions in particular are a full-up exercise in system mission design, resource allocation, deciding where to put your effort. They're places to try new and risky things. And I think most importantly to me, it's a very focused science team. You see here our picture from the Icing Glass campaign. It looks like everybody crammed into the room to take the picture, but for the most part, except I think for Mark Condi, who came in from across the hall, and this student who just came in for the picture, the rest of us basically lived in this room for 12 hours a day for 14 days during the rocket campaign. It's a lot of fun to work with a group of people who are really just focused on one thing. You learn a lot. So let's talk about the idea of distributed observations a little bit. Why? It's hard enough to launch a rocket. Why would you want to do it multiple times? And so the example that I typically use involves the idea of journalists near a tsunami. If you have one reporter on the coast and there's a tsunami, and over the course of a week, she walks away from the coast and she tells you that things are getting better. You don't know if they're getting better because it's been a week since the tsunami, or it's getting better because she's walking away from the coast. But if you had an array of observers all throughout the countryside, you could separate out effects of space and time. So this idea of mixing a partial with respect to distance and a partial with respect to time, you'd never do that in an equation, right? But we do it with spacecraft all the time. And usually you have one spacecraft and it moves across something, and when it sees something change, you have to decide whether you're looking at a spatial variant, a temporal variant, or some mix-up. And what I've found is that once you have one multiple point observation, you're always suspicious of single point observations thereafter. It really changes your view of how you interpret data. And the nice thing about auroral science is you can put, even if you have 4 or 32 or even 100 distributed observation points, the auroral ionosphere is pretty big. And having the benefit of auroral imagery to allow you to stitch those observations together is a huge plus. So, of course, the original distributed observation is the Ampere mission, based out of Johns Hopkins, using the Iridium array of spacecraft and the housekeeping magnetometers thereof. And so in each of these orbital planes, there are multiple spacecraft, and each of them record the delta Bs, which can be mapped into the auroral oval at this level. Other things that are going on these days are the explosive growth in the idea of small, low resource payloads. So the company Planet has 150 operating small camera payloads in low Earth orbit. Here's a day of the, or an hour and a half, I guess, of those payloads crossing across North America. And it's interesting to play with the idea of if you turned their cameras on over the Northern Lights, what might you see? And so here's a movie that my students made of the Themis auroral image, and then its conjugate mapped ideally to the southern hemisphere, and then a tracing of those spacecraft as they move through the image. From the sounding rocket world, one of the things my group has been doing is looking at the relationship between the in situ observations that we make with a rocket and the ground-based imagery observations. So here is where we've explored expanding a sounding rocket crossing of an auroral arc and an auroral image, and then replicating that crossing at many places along the visible arc to turn our line of observations into a two-dimensional field. Because the nice thing about electrodynamics is it follows rules. Maxwell's equations have to be true. And so if you have a set of observations in a distributed space, you can stitch them together from your expectations of how electricity and magnetism is supposed to work. So here's a cartoon cut into the page here. And so in a cross section of an auroral arc, there's a region where electrons are coming down into the ionosphere and making the light. There's a region where electrons are going back out, giving us our return current. And the closure currents that connect one current to another are governed by what's called the continuity equation, which tells us how the electric and magnetic fields and the conductivities down below need to be related to each other. And so exploring the distributed map of information of fields in the light of our expectations for electrodynamics allows us to try to understand how the auroral system works. In order to do that, we combine our observations, both our in situ and our ground-based observations, with physics-based modeling, and use those data to drive models to construct, for instance, a volumetric data cube of things like currents or densities. So I'd like to take you through a tour of a few different example science cases of how we've used these multiple point rockets to explore the auroral ionosphere. So here's half a dozen different cases. The first one being the hockey puck rocket from around 2000. And so this was the one where we had 4 small hockey puck sized payloads that each had a magnetometer. And again, we flew this through an auroral arc and looked at the delta B as seen by the individual payloads. And then you can explore, how would you interpret these data? So delta B as a function of time. If you just had one payload, all you could do would be to assume that you were flying across a current sheet and say that the variations you saw were spatial and that everything was uniform, except the gradients that you saw. And so you can calculate the field line current that would be consistent with that sheet-like assumption, or you can take the curl from the 3 that you have and calculate the field line current that would be consistent with that. And you find that not only do they have very different values, they don't even peak in the same places. So where the spatial curl is largest is not the same place as where the single point gradients are the largest. So as I said, once you have more than one measurement, it really changes your view of an individual measurement. Here's another example of a multiple point measurement in the auroral zone. This was from the auroral turbulence rocket. And for contrast, here you see a very sinusoidal clean pattern that's the same essentially on both payloads, right? Very different from this one. So here you can make an inference that says that what you're flying through with these separated payloads is actually a large spatial region that's varying in time. Another mission is called Cascades 2. You'll notice that we have 2s a lot of times in the names of our rocket: Auroral Turbulence 2, Cascades 2. Remember my list of, how sounding rockets go bad. And so one of the things we decided between Cascades 1, as it was, and Cascades 2 is that the only thing worse than doing it all over again is the idea of not doing it again. So you buckle down and you do it again. And so Cascades 2 was very successful. Again, this was a rocket out of Poker Flat, launched to the north towards Kaktovik. And here's an image of the auroral curtain as seen looking to the north. So this is the curtain that the payload array flew through. And so this payload had two payloads separated along the arc, and it also had two cowboys separated along the magnetic field. And so on this slide, I'll talk a little about what the separation along the arc could see. So if you look at this curtain off to the north, often you'll see rays traveling side to side along the arc. And what the Alaska group did was to take a slice through that image and generate a keogram. So this is east-west, and this is time. Come back. And as the sheared rays move side to side, the keogram shows this characteristic plaid pattern. So that was from the imagery. Down below here are particle measurements on the two separated payloads, and you see these bursts of field-aligned electrons that are almost but not quite the same. And so we can do coherency studies between the signatures and look for delays as we fly through it. And then put together a model space where we say that there are filaments of precipitation that are moving side to side and varying in time and dispersive, and say, can we reproduce both the visible signature and the measured electron dispersion signature to try and understand how this region, which is varying in both space and time, is fitting together. Another thing we could do with the Cascades mission was look at the plasma physics of wave generation. So remember, this had two of these cowboys, so these large 12-meter tip-to-tip. Actually, I'm not sure whether it was 6-meter or 12-meter tip-to-tip for this particular rocket. Nevertheless, very high integrity measurements of the electric field, and separated both along the field line and across the field line. These payloads have GPS on them, so we know exactly where they are and can take differences both in this distance and in that direction. And so what's shown here during that same region of rayed curtain is the DC electric field measurements from the two payloads projected along the distance between them and across the distance between them. If you cast that DC electric field as a flow, so E cross B over B squared, then you can calculate the shear between those 2 points. So the change in a velocity divided, so dv dx divided by x is a frequency, that's a shear. And you can look at the shear of that DC electric field as measured by this 2-point measurement. And that's what's shown here. And then you can look at the waves that were measured at the same time and show that there are wave enhancements in the ELF frequency range that are coincident with these measured shears. And so this becomes a valuable touch point for theorists working to understand the transfer of energy through different frequencies of waves. Another science case is our more recent rocket. So this is Icing Glass, which was 2017 out of Poker. And here is the Bob, the small payload. So unlike these large, high heritage electric field measurements, which to fly 2 of them was a huge effort. Here we're flying 4 of these very low resource small payloads that are Arduino based. They have not 12-meter deployable tip-to-tip electric field booms, but very simple RPAs that need to be interpreted in the context of other diagnostics. But nevertheless, what we can do now is we can fly an array of 4 of these. And so here we have a main payload with 4 separate bobs. So we have a 5-point array moving northward. And for this rocket, here you see a keogram as the rocket trajectory passes through a discrete auroral arc. At the top, we see the keogram. Here are the particle measurements. Here is the electric field and the magnetic fields as seen by the main payload. And as we come out the northern edge of this arc, there's a region of variation. If you zoom into that region, you see that it has a nice clean sinusoidal Alfvenic signature. And so an interesting thing to explore is what is the spatial variation of this region of variation. And so we have our 4-point measurements that are flying in a region that has the waves into a region that doesn't have the waves. And we can look to see what is the motion and definition of that boundary. Just to share here, these little sub-payloads have an inertial measurement unit on it, a little $35 IMU board like you might have in your phone. You can see the acceleration as the bob is kicked out of the main payload for the 4 separate ones. You see them spin up because they're rifled on deploy. That's how they stay stable. And then from modeling their separation, you can figure out their separation distance as a function of time. And so at around this time, each of the 4 payloads is about 400 or 500 meters away from the main payload. So we have a roughly kilometer square array of 5 payloads moving at 1 kilometer per second to the north. So what we can do then is look to see how that nice clean sinusoidal signature at the center payload compares to the smaller payload's cruder measurements coming through and leaving that region, and look to see when do the 4 payloads, 1, 2, 3, 4, cross through the edge of that region. And from that, we can optimize for the angle of this boundary and its motion as it moves south. And so these 2 pictures here look very similar, but they're actually 2 different things. This is a frame from the ground-based camera showing latitude and longitude with the trajectory of the rocket going across it. And this inset shows the 4 little payloads and the main one. Here you see the optimized angle of the boundary between the wave activity and not. That purple line is shown here. And you see that the apparent boundary of the Alfvenic oscillations is actually quite similar to the apparent boundary of the visible arc, which makes sense and is very satisfying, but they're actually 2 different measurements. One is the image of the precipitating electron boundary, and the other is the Alfvenic signatures that are measured. The other thing that comes out of fitting for those delays is the propagating motion of the boundary. And so this image over here is a cut through a sequence of these frames. It's a kilogram. So it's still latitude up the side, but it's time going to the right. And you can see that the equatorward boundary of this arc is moving southward over this time. And if you calculate the boundary velocity and lay that line on this same kilogram, you see that the apparent boundary motion parallels the motion of the southward motion of the arc. So we hope that these data will be useful to theorists who are trying to model Alfvenic behavior at the boundary of a current-driven system. The other thing you'll find that sounding rocket community is doing more and more, even from the conception of sounding rocket design at the beginning, is working tightly with physics-based modeling teams to interpret these distributed observations. And so, as I said before, we're working with a physics-based model called Gemini, and we use that model to stitch together our in situ observations and our visible observations into a computational data cube that we can use to explore questions, such as how do field-aligned currents couple to horizontal currents to obey current closure rules and Maxwell's equations in the lower atmosphere. We can take that data cube, right? So this is longitude, latitude, altitude, and we can slice it and look at densities. We can look at field-aligned currents in the Pedersen direction. I'm sorry, field-aligned currents, cross currents in the Pedersen direction, cross currents in the Hall direction, and explore our expectations for height integrated physics in the context of this volumetric data. One last thing I'd like to share about these campaigns. During the winter 2017 poker campaign, the auroral scientists there had the opportunity to share their auroral experiences with the community at Barrow, Alaska, through a virtual real-time panel with various rural Alaskan communities. And we heard and saw how that community viewed and thought about the aurora. Various elders in the community talked about how the aurora is part of their life. And then the scientists in their turn had an opportunity to talk about how the Northern Lights are part of our life. And I hope that we were able to communicate our passion about the Northern Lights in the same way that we were able to hear from the Alaskan community about what the aurora means to them. It was a very powerful afternoon. It really is a privilege and a joy to spend your working career studying the Northern Lights. It's a truism, but it comes up at just about every field campaign I've ever been on. Somebody will say, I can't believe they pay us to do this. So where are we going from here? I'll talk about two threads going forward. There are many, but here's just two. One of the things that our community is exploring right now is a concept study called ARCS. So this is an array of CubeSats. Remember I said that the Planet Company has 150 low Earth orbit CubeSats taking pictures of the Earth. The explosion in CubeSat technology has allowed truly distributed measurements as concept studies that are well worth exploring. And so this particular one is called ARCS, for Auroral Reconstruction Cube Swarm. And the idea would be to have a 4x8 array of small CubeSats in a tight swarm, so not spread over the whole globe, but a tight distributed swarm to look at the in situ parts of the ionosphere above a tight swarm of ground-based auroral imagery. So can we gather enough case studies to truly learn to understand how the in situ ionosphere is coupled to what we can see from filtered auroral imagery? We imagine making time-varying maps of plasma flow as this array comes across the arc, time-varying distributed maps of field line currents over the spatial scales of an arc like this one. We're using tomography between the ground-based cameras and the spacecraft to make a three-dimensional density profile. And then each of these cameras has multiple filters so that we can make maps not just of white light, but maps of precipitating energy and energy flux. And again, use all of these distributed data sets to drive physics-based models such as Gemini and GITM to what we call decode the aurora, and exploring the relationship between visible aurora and distributed currents and flow fields for critical physics of the auroral ionosphere at arc scales. And I have to say that this is a large, it's not a sounding rocket mission, it's a larger satellite-based mission, but it has grown out of the tight community of the sounding rocket world. Another thing that's ongoing is yet another crazy sounding rocket. And so we're all plowing ahead this winter trying to build a rocket called Kinetics under Peter Delamere's guidance. He's a scientist at University of Alaska Geophysical Institute. And the Kinetics rocket is exploring basically the Io spot. So remember, Jupiter has moons, moons have volcanoes. So the Io moon of Jupiter spews volcanic gas. That gas escapes into the Jovian magnetosphere and ionizes. It grabs onto the magnetic field lines of Jupiter and twangs it like a guitar string. And Alfvene waves go down to the surface of Jupiter and make a spot. And so the Io spot is a clean, very well studied feature of the Jovian magnetosphere. And so what this sounding rocket is trying to do is to replicate that over Wallops Island. And so the idea is to release a bunch of neutrals, let them ionize. As they ionize, they grab the magnetic field line and twang it and make an Alfvenic profile. So how might you study that? Well, as in the picture that I showed at the beginning, you release a payload that has barium in it. You let it get away from you and explode and make a barium impulse. And then you have a set of diagnostic payloads. And as the disturbance passes across that array, you measure it. And so here's one of Peter Delamere's models of the expanding barium cloud. Here is the barium and the field line, and here's the little set of 5 payloads that we're going to be, and we will be watching this expand across it. So this payload has a main payload that has signatures like porcupine. It's got booms in all directions coming off of it. It has 2 separated chemical payloads, and it has 4 of these little bob payloads. So it has 1, 2, 3, 4, 5, 6, 7 payloads. It's a 7 payload study. It'll launch from Wallops Island, hopefully early this spring. There will be an airplane over Bermuda and cameras looking from various directions to study the behavior of this system. So the crazy people who build multiple point rockets are still at it, and we're working away. So let me finish with a summary of the premise. I think the sounding rocket world is a lot of hard work, but it's very satisfying. It's fun to do stuff. It's fun to expose students to building things. It's fun to build stuff yourself and to test it and have it work. It's also very useful. It provides a lot of science, and it also seeds many larger projects. The FAST satellite that studied the aurora is a case in point. You learn a lot from the science call process of launching an auroral sounding rocket. It's an exercise in real-time space weather. It makes the evolution of the ionosphere and the magnetosphere very real and very personal. It's not something you're just reading about in a textbook. You're watching the ionosphere evolve and trying to predict what's going to happen in the next 10 minutes and whether it's time to launch your rocket. And it also generates a tight community of people who have worked together intensely on projects, and that's a very valuable experience. So I'd like to thank the Sounding Rocket community. When I had the opportunity to give this talk, I asked for people what they wanted me to say, and in particular, Rob Pfaff, Steve Powell, and Miguel Larson sent me oceans of images and pictures and photos of things. It's been fun to explore what we've done in this field. The communities at Poker Flat, at Andona's Research Range, and most particularly at Wallops Flight Facility, they have our back. They're why what we do works. And finally, the many, many students who have worked on this, I have my thanks. And that's all. Thank you.